Hey guys, welcome to today's class. I hope you guys have a wonderful day. But let's get started with our question. Let's start with problem 10. How many different even natural numbers, each containing three different distinct digits, can be written using just the digits 0, 2, 3, 5, and 8? A 6, B 12, C 20, D 30, and E 36. Notice that 0 cannot be the first positive integer. And there are three different digits that can be at the last: 0, 2, and 8. So we want to find how many can be written. Right? Let's think about this first. We can choose three digits for the last one. Three total digits. And notice that for this digit, we have four choices. We have four choices. We can just rearrange the remaining. It's because of 4 times 3 times 3. Oops, my bad. It's not five digits. So make sure you're reading the problem carefully. We want to find, we have three digits. We have four choices for the first one, three choices for the last one, and 3 times 3. So that's what we had to do. That's basically the answer, but we were overcounting on one part. Notice that we have to subtract the numbers with, I have a 0 in the hundreds place because we didn't, well, we technically counted, but we overcounted with the 0 and the tens digit, I think. So if we put it over here. Wait, hold on. Let's count again. We have 5 total digits and we want a 3. And notice that we have to have 4 in the first, 3 in the second, and there's 3 in the third. And we're overcounting on the 0. On one of the digits, one of these, there's 6 possible ways in which this doesn't work. Because we might have double counted where there's a 0 over here and there's a 0 over here. And we do not want that. That's a total of 6 possible ways if we were to do it. There's 6 possible ways. So the answer is just 36 minus 6 or 30. Or D as our answer. Alright? Now let's move on to problem 11. Let's guys have a go with this question and turn my answer to chat. So about the first one question, I meant to say it was the hundredth digit, so I was self-doubting myself. So make sure you're confident in your answer. And we want this 3. I kind of forgot that you couldn't. We already counted for the even, so the 0 could be on the hundredth place, and that's where you get the 6 because the 0 cannot be in the hundredth place. Okay? Sorry about that confusion. But now let's move on to problem 11. But let's get started with this question. So seems like nobody got it right. So let's get started. And how many ways can four married couples proceed in a round table if no two men, as well as no husband and wife, are to be in adjacent seats? Why? So there's basically we can just we know that since there's rotation into it, we have normally we would have 4 factorial minus normally to see 4 women or men, we would have 4 factorial in a row. But it is in a circle. So we have to divide by 4 to account for the rotation since there's 4 women. Okay, so now let's say we do the woman first. Now we would have 3 factorial place the woman. Now let's talk about the men. Now, say we have the 4th male who has the 4th wife. He has 2 ways to sit. 1, 2, 3, 4. He has 2 ways. 1 and 2. Directly opposite. Now, after he is seated, any one of the 2, the other men basically have only one way. Why? We'll see. So this is the first woman, right? The first woman. We let the male sit over here. Now can you see? Well, these ones, the male that's married to the first female, we have 2 of them that's already next to each other. So there's only one choice, or between 4 and 3. Similarly for the other 2. So that just gives us and multiplied by another 2 ways. This just gives us a total answer of 12, or B. Alright? Now let's move on to problem 12. In the figure above, each line segment represents a one-way road with travel permitted only in the direction indicated by the arrow. How many ways different routes from A to G that pass through E are possible? Oops. Sorry about that. For the problem 11, notice that. Let me re-explain what it says. Notice that if we have n for any circle of n objects or n people, the total number of ways to order is n minus 1 factorial. So you have to divide by n to account for the rotations. Like, for example, say we have A, B, C, D. It's the exact same thing as D, A, B, C. Or C, D, A, B. Right? So we start with 3 factorial. Let's first order the ladies. Or we can order the males. But it doesn't really matter. So, after this, let's say we order the ladies first. We only have the men left. Let's say the first man just to choose where he sits first. There are 2 ways to do it. There's one over here and one over here. Alright, let's say he chooses this spot, right over here. Now, let's look at the second male. Or the third male in this case. I meant 4th male. Like this one. We'll look at the 4th male. There's one way to place it. Where? Over here. Why? Because notice that this place and this place are next to the female. And we do not want that. So all we have left is to place it in here. Similarly, for the others, it follows. So the answer to this question is just 3 factorial times 2, or 6 times 2, or 12. Right? Now let's move on to problem 12. Let's go ahead and go with this question and turn your answers to chat. Alrighty then, let's get started with this question. Let's get started with this question. Okay, so notice that how many different routes from A to G pass through E are possible. We noticed that we want this to be part of the path. So all we actually have to do is notice that this path over here, this path over here, you see this path? That is not included. We do not need to include this. This is a restricted path. From F to G, we do not need, and it's restricted because we do not need to count it. So all we have to do now is just count how many ways are there to E. This is much easier than counting how many ways are there to A to G. Well, slightly easier. Any way to simplify this further? Well, these arrows basically point to D most of the cases. So might as well start counting with D, right? Now we know that the edges do not include D, quite obviously. So we might as well count this. But you can see that the rest of these paths include D. So we already have two down. We just need to add the rest that go through D. Now this is just through counting. There's one map path. Oops. There's one path that goes from A, B, D, E. Another goes A, D, E. Another one goes A, B, D, F, E. Another one just goes A, C, D, F, E. And there's more. So you can just count it, and they're gonna come out as a total of 6. So adding this up just gives you 8, or E as your answer. Alright? So basically, here's just casework. Now let's move on to problem 13. 10 points are placed on a circle. What is the greatest number of different lines that can be drawn so that each line passes through 2 of these points? I was gonna have a try on this question and tell me answers to chat. All right, then let's get started with this question. So basically, how do we do this? Notice that we can assume, in this case, we can assume that no 3 points are clean. Why? Because we want the greatest number of different lines. Well, this can happen if we have choose 2 points out of the 10, or 10 choose 2. Remember, this is just 10 times 9 divided by 2, or 45 possible lines we can draw. Why? Because 2 points can define a line. Right, so the answer to this question is just D, 45. Let's do problem 14. 4 lines are drawn in a plane so that there are exactly 3 different intersection points. Into how many non-overlapping regions do these lines divide the plane? You guys have a try on this question and tell me your answer to chat. A hint is you can just draw a diagram. All right, guys, let's get started with this question. So four lines are drawn on a plane so that there's exactly three different intersection points. So how many non-overlapping lines do these divide? How many non-overlapping regions do these lines divide the plane? In normal scenario, we can just draw a circle to represent the plane, all right? Or in this case, normally you can draw a circle if you want. It makes easier visualization. In this case, we will not. Actually, we are. Now we're gonna draw four lines, all right? Four lines. We want three intersection points only. There's one intersection point, two, two intersection points, and still one, and three intersection points. How many regions do this divide to? There's 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, but can we get a better answer? How many can we get a better one? Let's try again. There's four lines. 1, 2, 3. No way to put the fourth one. So there has to be two, and so there has to be a three concurrent one. 1, 2, and 3. Oh, what if we were to put one like this? Alright. Now we just want a third intersection. Okay? We can just do this and do this. But that just gives you 1, 2, 3, 4, 5, 6, 7, 8 intersections. In this case. That is four lines technically. But there is an exact formula. The formula is n to 0. This is the formula. N choose 0 plus n choose 1 times plus n choose 2. So it's just 1 plus n times n minus 1 divided 2. We want to choose the optimal. This is the formula for the most optimal. As you can see, trying to draw a diagram is gonna take forever. So we just apply a formula. Now plugging in four lines, so n is 4. We get the answer of 13, or D. Alright, now let's move on to problem 15. The 4 points P, Q, R, S lie on a line L. The 5 distinct points T, U, V, W, X lie on a different line that is parallel to the line L. What is the total number of different lines that can be drawn so that each line contains exactly 2 of the 7 points? Well, there is a total of 20 ways. Why? We just select 4, choose 1. We just select 1 from the 4 over here, and 1 from the 5. That's just 5, choose 1. Is equal to 20, or D. Alright, now let's do example 16. In how many ways may we distribute 7 different books to Alex, Bob, and Catherine such that Alex and Bob each get 2 books and Catherine gets 3 books? Let's go have a try on this question and tell me your answer through chat. All right, let's get started with this question. So basically, we have 7 different books, right? We have 7 different books. And we have to give 2 to Alex and Bob and 3 to Cassie. How do we do that? So remember staff, they're different books. Okay? So we can do 7 factorial or 2 factorial against 1, 2 factorial and 2 factorial. Or 210. Right, from the formula we had in last class, is 7 factorial divided by 2 factorial times 2 factorial, 3 factorial. And a refresh, n sub 1 all the way to n sub n. We sum that up is equal to n. Then the number of ways to arrange it is just n divided by n sub 1 factorial all the way multiplied by 2n sub n factorial. The answer to this question is just D. Now let's move on to example 17. I'll let you guys have a go with this question and tell me answers to chat. Alright, guys, let's get started with this question. So how many different ways can all the letters of Indiana can be arranged in a line? Assume that duplicate letters are indistinguishable because they are. Right? Same exact thing. Kind of the same exact formula, all right? There's a total of 1, 2, 3, 4, 5, 6, 7 total letters. 7 factorial. All right. On the bottom of the denominator, we have to divide by the duplicate number. So for I, there's 2 duplicates. For n, there's 2 duplicates. So divide by the number for each letter that's duplicated. Divide by how many duplications. For example, I is 2. So we write 2 factorial, right? For example, it was 5, then we write 5 factorial. Same for n, 2 factorial. Same for a, 2 factorial. Dividing and do the multiplication all out, we get 7 factorial divided by 8. 7 factorial divided by 8 is 630. So the answer to this question is D, 630. So in general, if we have n letters, and then we have duplicates, so we have n factorial, divide, say, for the first letter, there was n1 factorial duplicates. Second one, n2 factorial duplicates. We multiply that until the last number of duplicates, say an n factorial, or nk. Say there's the kth one. The kth letter has n sub k duplicates. We get n sub k factorial as the bottom, as the last one. That's the formula to counting how many letters arrangements are possible. Alright, that's it for this class. I hope you guys have a wonderful day, and I'll see you next week. Bye.